The last video or couple videos was probably a little bit overwhelming to you. I know it felt overwhelming for me to make. The good news is all we have left to do in this section are examples. And examples generally are nice from the student's point of view, and they're definitely nice from the teaching point of view, because it involves a lot less thinking. I don't have to worry about how to teach something. I just kind of go through and solve some problems. So that's what we're going to do. This first question says, let f of x equals x cubed plus 6x squared plus x minus 5. And what we're being asked is to find capital F of x. Remember that capital F of x is defined to be the antiderivative of little f of x. So really you could translate this question into figure out the antiderivative of this expression, x cubed plus 6x squared plus x minus 5. When you see this question, it'd be nice if you were able to view this as the sum of 4 different terms, and at least one of those terms has a coefficient. And you might be wondering what I mean by that, at least one of those, but I'll explain shortly. The antiderivative of a sum of terms is just the sum of the antiderivatives. That's this rule right here. So we just break this one hard question up into a bunch of easy questions. We ask ourselves the question, what's the antiderivative of x cubed? And then we're going to add to that 6 times the antiderivative of x squared. And then we're going to add to that the antiderivative of x. And then finally from that, we're going to subtract the antiderivative of 5. 4 questions, let's take them one at a time. This first one here, the antiderivative of x cubed. Well, the idea is to use the power rule. And you can just memorize the power rule if you want. I mean, it's written up here. Here's the derivative form of it. I'm sure I wrote the antiderivative form somewhere. I guess it would be this one right here with this little caveat. It says the antiderivative of x to the n is equal to 1 divided by n plus 1 times x raised up to the n plus 1 power. But for most students, that's kind of a mouthful and kind of a lot to memorize. It's a little bit easier to just sort of think about what's going on. If I want to end up with x cubed, I better start out with x to the 4th, because if I'm using the power rule for derivatives on x to the 4th, I'm going to subtract 1 from this exponent. That'll produce the x cubed. But it won't just produce x cubed, because I'd be bringing that 4 down in front. So it would produce 4x cubed. But I don't want 4x cubed, I want 1x cubed. How do I change 4x cubed into 1x cubed? I divide by 4. The antiderivative of x cubed is 1/4 x to the 4th. You could argue that I should tack on a plus c right here, but I'm not going to, and I'll explain why later. This next question, the 6 is not inside this antiderivative symbol, so I just leave it alone, and I take the antiderivative of x squared. The antiderivative of x squared, I'm going to add 1 to that exponent to get x cubed, but then I'm going to recognize that I need a 1/3 out in front so that I don't end up with 3x squared, I end up with x squared. What about the antiderivative of x? It's kind of the same idea. Think about this as x to the 1 power. So I want to make it x to the 2nd power, because if I was going to take the derivative, I subtract 1 from the exponent, and that gives me the x to the 1 power. But as you know, the derivative of x squared is not x, it's 2x. So I need this 1/2 to make sure everything kind of balances out right. What about the antiderivative of 5? Well, we haven't really talked about that. I mean, technically I've given you enough information to figure that out, but not directly. Using the rules that I've taught you, to figure out the antiderivative of 5, you'd have to be kind of clever and recognize that you could think about 5 as 5 times 1. And then you could take that 5 and pull it out in front of the antiderivative symbol. So it's really just 5 times the antiderivative of 1. And then maybe if you picked up every single one of these rules that I mentioned, you'd be like, the antiderivative of 1, isn't that just equal to x? I'd be like, yeah, exactly right. Good for you. So I guess this would be equal to 5x. Technically 5x plus c. And that's all entirely true, but I don't know anyone who solves these this way. Instead of factoring a 5 out in front of the antiderivative symbol and using the fact that the antiderivative of 1 is equal to x, what might be easier is just to remember anytime you're taking the antiderivative of a constant, tack on your variable to give you this negative 5x. Maybe we can call that an optional rule. An optional rule that would replace the fact that the antiderivative of 1 is equal to our variable x. We could say that the antiderivative of any constant is just equal to that constant times x. This might be a more useful form to cut out extra steps and allow you to go straight from this line down to this line. Now we have the annoying thing to not forget to tack on a plus c. Technically, there's lots of different c's, but the sum of all these different arbitrary constants is just some arbitrary constant. This c represents any number I want it to represent, so I can just put a plus c at the end. Not a horrible idea to clean this up a little bit, so I'm going to go ahead and do that. But we're done with the calculus at this step. 6 times 1/3 is just 2, so I got 2x cubed. I think everything else I'll just kind of leave it alone. Not a horrible idea, especially while these are still kind of new to you, is to check your answer. How would you check your answer? You take the derivative of that answer, 1/4 x to the fourth plus 2x cubed plus 1/2 x squared minus 5x plus c, and make sure that you get back this thing in here that we're taking the antiderivative of. It's a little bit annoying for me to keep saying this thing right here that we're taking the antiderivative of. Turns out that does have a name. It's what's called the integrand. The entire thing is the integral. The expression we're taking the integral of is called the integrand. You don't really need that vocabulary, but just FYI. Let's do another example. What's the antiderivative of 4e to the x minus 5, which is what this is asking when it says little f of x equals 4e to the x minus 5, and we're supposed to find capital F of x. Well, we could certainly switch the notation. We could be like capital F of x is really just asking me to take the integral of this expression 4e to the x minus 5, and to take the integral of 4e to the x minus 5, maybe I would recognize that I have two different terms here, so I'm going to make this two different integrals. One of those terms has a coefficient of 4, so I can make this 4 times the integral of e to the x minus the integral of 5. The nice thing about each of these integrals is they're fairly easy to figure out. The antiderivative of e to the x is just e to the x, so I get 4e to the x over here, and the antiderivative of 5 is 5x, because anytime I'm taking the antiderivative of a constant, I have to remember to tack on a variable. I should tack on a plus c so I get the antiderivative, not just an antiderivative. This would be my final answer. 2 more examples, and I'll save the last 3 examples for another video. This one's a little bit clever, I guess. A little tricky. I wouldn't expect students to be able to solve it, but once you see how I solve it, you'll be like, oh, that really wasn't all that hard. I don't know, tricky, not hard, I suppose. Again, we're looking for capital F of x, so we want to know the antiderivative of this expression. Maybe you'd recognize that this 2 right here can be treated as a coefficient. We can think about this as 1/2 times 1 over sine squared x. And coefficients can be pulled out in front of the integral symbol, so I could move that 1/2 down in front. But then you're like, but what about the 1 over sine squared x? Like, what do I do with that? And if you stare at that for a long time and have no idea what to do with it, good, that's probably where you should be. If you got an A in your trig class back in the day, maybe you'd think to rewrite sine squared x as cosecant squared x. Because 1 over sine of x is the same as cosecant of x, 1 over sine squared x is the same as cosecant squared x. And if you were lucky enough to think about that way of rewriting this trig expression, maybe you'd be like, wait, cosecant squared x, that kind of rings a bell. I feel like that was an answer at one point. Cosecant squared x, cosecant squared x. Where have I seen that before? Oh, cosecant squared x. That's almost the derivative of cotangent of x. So I can use the fact that the derivative of cotangent of x is equal to negative cosecant squared x to come up with the fact that the antiderivative of cosecant squared x is equal to the negative of cotangent of x. Again, I said these were optional-ish, so it's a little bit unfair to hold you to that standard of recognizing that equivalence. But if you did recognize that, we could replace the antiderivative of cosecant squared x with negative cotangent of x, tack on our plus c, and be done with this problem. I probably wouldn't leave my answer that way. Maybe I'd write it as negative 1/2 cotangent of x plus c, or negative cotangent of x divided by 2, whatever you want. The point of this problem was just to show how these trig antiderivatives can be a little bit tricky. And when you run into something like 1 over sine squared x, you might have no idea where to go. And my hint is, see if you can rewrite it into an equivalent form that maybe looks a little bit familiar. One more. Find any function f of x so that f prime of x equals 1 divided by x times the natural log of 2. Okay, when it says any function f of x, it's kind of a weird question. What's implied in here is that there's multiple correct answers. What we're looking for here is an antiderivative as opposed to the antiderivative. The only difference being, I don't have to worry about tacking on this plus c here. So I got 1 divided by x times the natural log of 2. How would I deal with that? Well, one option is to view this as 1 divided by the natural log of 2 times 1 over x. And if you can do that algebraic manipulation, it might be a little bit easier for you to recognize that this, although it doesn't look like it, is just a constant. There's no variables in here. This thing is just a constant. So it's serving as a coefficient. I can take that coefficient and pull it out in front of my integral symbol. I got 1 divided by the natural log of 2 times the antiderivative of 1 over x dx. And here it's tempting to be like, ooh, 1 over x dx, I can deal with that. I'll think about that as x to the negative 1 power and I'll use the power rule. Be like, no, don't do that. Negative 1 is the only exponent on x that you cannot use the power rule for, right? Remember that special case? We didn't need any caveats for the power rule for derivatives, but the power rule for antiderivatives works for any value of n except for negative 1. And unfortunately for you, the value of n that you have down here is negative 1. This is x to the negative 1 power. So what do you do if you're not going to use the power rule? You have to think about, when was this an answer when I was taking derivatives? And the answer to that question of when was this my answer when I was taking derivatives is when you were taking the derivative of the natural log of x. The fact that the derivative of the natural log of x equals 1 over x almost means that the antiderivative of 1 over x should be the natural log of x, but because of some kind of complicated stuff about undefined values and restricted domains, I have to tack on these absolute value symbols. What I'm saying is the 1 divided by the natural log of 2 is doing just fine. I'll leave that alone. The antiderivative of 1 over x is the natural log of the absolute value of x. I could tack on a plus c if I want, but when they ask the question this way, where I'm just supposed to find any function, so I'm just looking for an antiderivative, probably don't want to tack on a plus c because then you're giving the antiderivative. I mean, if you want, you could tack on a constant plus 101, sure. Be kind of funny about it, like the derivative of this is this, therefore an antiderivative of this would be this, and that's entirely correct, but I think most people wouldn't. Most people would just be like, this is good enough, this is my answer, let's move on. And we will move on, but I think I'll move on in the next video. I got 3 more examples to do, but I think they're a slightly more difficult variety, so I'm going to save those for a new video.